Welcome to this lecture series on pulse width modulation for power electronic converters, where we have been dealing with pulse width modulation for different kinds of DC-AC converters essentially. So, we have had these various course modules which are like overview of power electronic converters and applications of voltage source inverters and so on and so forth. So, after that we looked at the purpose of pulse width modulation and the low switching frequency PWM, how to produce it at low frequency. This is something we will look at again today in the context of pulsating torque. And in the next two things we looked at the PWM generation at the higher frequencies. I mean, when the switching frequency of the inverter is significantly higher than the fundamental frequency, you generate it by comparing 3-phase triangular carriers, I mean 3-phase modulating signals against a triangular carrier, or you go by the space vector approach, where the voltage vector is provided to you as a revolving voltage vector, and you sample that and you try to synthesize an average vector equal to the reference vector in every subcycle. Go about doing it now. So, these two modules are essentially on the generation at the higher switching frequency side, and from now onwards we have started looking at the waveform quality aspect. For example, this line current ripple is one aspect of waveform quality. You want to produce sinusoidal currents. So, you want to apply a sinusoidal output voltage, however, your inverter has harmonics also. The harmonics lead to harmonic currents, and therefore, you have certain current ripple, which is actually the sum of all the harmonic currents. So, we tried to analyze this line current ripple. We mostly did it in the space vector domain, and we would we try to get some measure for the RMS ripple current that is flowing through the line. Then in the subsequent module, we looked at the DC side, we looked at the DC link current. This is the last couple of lectures we did this now. How is the DC link current, and then to understand the nature of the current that flows through the DC capacitors also. So, once again we come back to analysis of torque ripple, which is again on the waveform quality aspect now. This is kind of closely related to the line current ripple. So, here you are worried about the harmonic currents produced by the harmonic voltages. Here we are worried about the harmonic torques produced by the harmonic voltages now. So, you have harmonic voltages, the harmonic voltages produce harmonic currents as well as harmonic fluxes. So, because of that you essentially start getting pulsating torque. If only fundamental current were flowing through that and there are only fundamental flux in the machine, there will be a fixed torque, there will be no ripple. So, because of harmonics in the fluxes and currents, they are actually your ripple now. So, today we will start with that now. So, to analyze the torque ripple, we will look at two situations primarily, that is, one is we will look at low switching frequency, that is when really the pulsating torque is pretty much high, and we will also try to extend it at the high frequency side, and we will extend the analysis of the line current ripple to the analysis of torque ripple. So, this lecture, that is in today's lecture, we will predominantly focus on the low frequency aspect, and in the coming lecture we will focus on the higher switching frequency case, and we will do some analysis similar to what we did for line current ripple and go for torque ripple. So, for now we are now going to look at low switching frequency PWM and analyze the pulsating torque now. So, that is why I said that there is going to be low switching frequency PWM. We might have a quick review on that if necessary, and then we will look at the voltage, current and flux harmonics when you are feeding an inverter, not just the sinusoidal voltage, but also the harmonic voltages. The harmonic voltages are going to generate harmonic currents in any load, and in a motor harmonic voltages are also going to lead to harmonic fluxes. So, we will first take a look at those harmonic currents and harmonic fluxes, and we will develop some idea on what kind of revolving magnetic fields they produce, what the fundamental produces and the harmonic produces. So, you should remember that the fundamental component, there are 3-phase fundamental component, they are 3-phase sinusoids, they produce a revolving magnetic field. You take any other harmonic voltage also, like the 5th harmonic voltage or 7th harmonic voltage, that is also a 3-phase balanced sinusoidal voltage, but it is just at a different frequency and it might have a lower amplitude. So, it will also produce a revolving magnetic field. So, that is something we will try to get an idea about. So, an idea about the harmonic mean the revolving magnetic fields produced by harmonic voltages. So, then we would try to understand the steady state torque produced by the fundamental components like the fundamental flux and the fundamental current alone, and we look at the pulsating torque, which normally comes from by the interaction of the fundamental flux and the harmonic current, and the fundamental current and the harmonic flux. And then we would also probably try to say try to do how you can do a selective elimination of harmonic torque. You might recall when we did this low switching frequency PWM earlier, we looked at what is called as selective harmonic elimination. What we tried to do is we tried to produce a PWM voltage waveform which gave us the necessary fundamental voltage, but eliminate a specific harmonic voltage. We call that as specific elimination of harmonic voltage or specific selective harmonic elimination. Now what we do is we will try see how we can selectively eliminate an harmonic torque. We will get some idea on how to do about it now. Then in the subsequent lecture most probably we would move into this high switching frequency PWM, and we will try to do the analysis of pulsating torque in the space vector domain, and maybe have a comparative analysis of different PWM techniques, and possibly design a space vector based PWM technique for reducing torque ripple. So you might recollect that in space vector methods we had apart from the regular conventional space vector PWM and bus clamping PWM, we also had some advanced bus clamping PWM methods. Some of them can actually contribute to reducing the torque ripple. That is something that we could see in the next class. So now I would call this as analysis of torque ripple in induction motors 1 with particular focus on the low switching frequency. So this is the voltage source inverter which we have been seeing over the last several lectures, and the motor, now in this case we are now clearly looking at a motor being connected. These are the RYB terminals of the motor. So the motor is not shown here, and this is the DC side. There is a DC voltage of VDC applied here, and this is the DC midpoint O. So you can look at some examples of low frequency PWM waveforms. Remember, these have actually been given in the context of a single phase inverter, but it does not matter. So let us say you have an AC load, but you have a DC voltage available. What you can do is you can apply this DC voltage initially and then with a sine reversal like this and go about doing it. So you can apply it as a square wave through an inverter. So what could be called as a square wave single phase inverter, and you can produce such an output across this. Now as we have already seen, this has a fundamental component. If this is V, that fundamental component will be 4V upon pi. That would be the peak value of the fundamental component. We will just go over it and come like this part now. So in case you want me to draw that, I can do that. So it will have a fundamental component, it will go slightly higher than that and come back and go and take it over like this. Okay. Yeah. So you cannot control this fundamental voltage, and that is the reason why you would want such kind of pulses. So by such pulsation, what you can do, you can reduce the fundamental amplitude like what I have shown here. These are all certain things we have discussed in good detail when we did the purpose of PWM and the low switching frequency PWM now. So the second waveform gives you some way of controlling that, but it still has a high harmonic content. So the third waveform, for example, can give you a very good way of controlling the fundamental voltage, and also it controls the harmonics much better. You can see that you look at the sinusoids, it will be very clear that the pulse widths are equal here. Here the pulse widths are modulated in a particular fashion. Incidentally, they are modulated in a sinusoidal fashion here. The width is very high and it is low, it varies in a sinusoidal fashion, and you will see that the fifth harmonic could be very high here, for example, whereas in this case that will be pretty low. So the harmonic content improves. So the lower frequency harmonics we are able to reduce significantly. It will result in a very good quality waveform, current waveform through the load. So these are certain examples of low frequency PWM, which you can look at it these as possible outputs of single phase inverter. Now let us take an 3-phase inverter's output, some typical voltage low switching frequency PWM waveform. So I have not indicated the harmonic orders here. We are trying to look at some low voltage harmonic spectrum of some low frequency PWM. So it is switching at some frequency, there is some PWM waveform being produced. So the PWM waveform, then the voltage waveform that is applied, we are looking at the inverter's output. So the line to line voltage will not have the third harmonic, etc. First what you find here is this is the fundamental component. This is the fundamental component. Then you have 5th and 7th harmonics. Then you will have 11th and 13th harmonics. Then you will have 17th and 19th. If necessary, I can write them for you. Write it down. This is 1 fundamental. This can be 5 and 7. And this would be 11, 13, this would be 17 and 19. So this is the harmonic order n, and this is the amplitude of any harmonic voltage, we will call it Vn. So this is just a typical waveform that you might have, where this is the PWM waveform has been represented in terms of this. So what you want is only some fundamental voltage, whose amplitude may be called as V1, but what you are getting is all this. V5, V7, V11, V13, V7, V19, etc. also getting applied on the load. So this V5 is certainly going to cause some I5 when applied to a linear load. this V7 is going to cause certain I7 when applied to a linear load. So, this is all going to cause 5th harmonic current, 7th harmonic current, 11th harmonic current, 13th harmonic current and so on. For example, when you feed them to an RL load. Now, we are going to feed it to an induction motor load. So, this will also produce in an induction motor also this 5th harmonic voltage will produce 5th harmonic current, 7th harmonic voltage will produce 7th harmonic current. Not just that, the 5th harmonic voltage will also produce a 5th harmonic flux, and the 7th harmonic voltage will also produce a 7th harmonic flux. So, we are going to take a look at these current harmonics and flux harmonics, review the current harmonics rather and look at the flux harmonics in some detail today. So, if you want to look at what is the effect of the applied voltage, the applied voltage has a fundamental component and has harmonic components. So, as far as the fundamental component is concerned, it is a sinusoidal voltage. It is, you can look at the per phase equivalent circuit. It is a, the fundamental is balanced a 3 phase sinusoid. You can look at the per phase equivalent circuit of the induction motor. This is the rotor side, this winding resistance and the leakage inductance. This is the magnetizing inductance. This is for the stator, and this is the rotor's leakage, and this is the rotor resistance RR versus the slip. As you know, slip is what is slip? This is synchronous speed minus the rotor speed divided by the synchronous speed. So, the rotor does not rotate at the synchronous speed, it rotates slightly lower than that. A measure of that is the slip now. So, this is the fundamental equivalent circuit. So, you can apply your fundamental voltage to this, and whatever current drawn by this circuit is the fundamental current that you should expect your motor to draw. This is something that we have seen even before. Now, if you apply the harmonic voltage, you consider some nth harmonic voltage, this is Vn, and the machine model now reduces to Ls and Lr. As we have seen also in earlier cases, what happens when you are applying a harmonic voltage, the slip is very high, close to 1. We will also probably have a chance to relook at it now today in a short while from now. So, this S normally for the fundamental will be very low, like 0.02, 0.03, therefore, RR by S will be very big. Whereas, for harmonics this S will be almost close to 1, and therefore, RR by S is almost RR, and which is actually a small quantity. So, this is effectively for the harmonics it is Lr, and Lr coming parallel with Lm, Lr is very small, and therefore, it will dominate over Lm, and therefore, you have only Lr. And once again at high frequencies this reactance is going to dominate over this resistance, and therefore, the motor will be effectively seen as only the sum of its two leakage inductances, and that is what is shown here. So, it is just the two leakage inductances, and it is a model, it is a harmonic model of the induction motor or harmonic equivalent circuit. And this equivalent circuit, if Vn is your amplitude of the nth harmonic fundamental, Ls and Lr are your leakage inductances, Vn upon n omega times Ls plus Lr is going to be your nth harmonic current amplitude. So, this gives you a very convenient way of calculating what is your nth harmonic currents now. So, let us slightly get into the details of the motor now. So, this is the stator winding, the outer side is stator, and you have the windings, the conductor sitting in the inner periphery of that, and this is the rotor, and what you have in between is the air gap. Okay. So, you look at this is your R phase winding, that is the coil is going, coming out, maybe going, coming like this, and then going there, and then coming like this now. So, it goes on like this. So, effectively what happens is, this is a coil whose axis is like here, and this is your Y phase coil. I have shown it in green color instead of yellow color, right. So, this is like a coil, this goes around like this, so wound around. So, this is like a coil whose axis is something of this nature, and then you look at the blue phase, they are indicated in blue colors now. So, you have the coil running around like this, there is something on here, and there is a at the end it goes over. So, this is like a coil whose axis is in this direction now. So, the 3 phase axis are actually like this. So, you have the R phase axis, you have the Y phase axis, and you have the B phase axis. And for the purpose of analysis, we always, of course, we have a machine which has 3 windings and along 3 axes like this. It is possible to think of the machine as one having just 2 windings, call them alpha and beta along these 2 axes. So, what we have seen before is we can excite this with some 3 phase voltages. Here we can excite them with so called 2 phase voltages or 2 phase currents, both sinusoidal at the same frequency, have a phase shift of 90 degrees now. So, a 3 phase machine can be seen as an equivalent 2 phase machine. So, this is further here. So, how there is a revolving MMF which is produced by the 3 phase winding, something the same job can be done by the 2 phase windings also. So, whatever IR, IY and IB when applied will do that, the same job can be done by I alpha and I beta. So, winding axis, but here you see the winding axis are separated by 90 degrees, and they should be excited by currents which are also phase shifted by 90 degrees in time. So, we have seen this, we just are having a review of this. So, that we can look at the space vector transformation which we will need in a short while from now. So, the 3 phase windings are the axes are represented by these arrow marks here, and this can be the MMF here, and this alpha beta, there are the 2 winding axes, this is the MMF now. So, you can look at this MMF as a result of the currents flowing through R, Y and B windings, the same MMF being produced by currents I alpha and I beta flowing through alpha and beta windings now. So, you can equate this Ni alpha, that is along the alpha winding, which is a n number of turns, certain current I alpha flows, and that produces certain amount of flux, which is actually equal to NIR cos 0 plus NIY cos 120 plus NIB cos 240. And again there is this beta axis winding, and there is some beta I beta current flows through that produces an MMF Ni beta in this direction. The same thing is produced by the 3 phase winding as given by here, NIR sin 0 plus NIY sin 120 plus NIB cos 240. I mean this should be sin, I am sorry, there is an error here, please change it over to that now. Okay. So, yeah, thank you. So, you can write down the space vector transformation like this. I alpha can be equated to IR with the condition that IR plus IY plus IB is equal to 0, it is a 3 wire load. So, this is your I alpha is related to IR, I beta is related to IY and IB like this. Thus, the 3 phase currents IR, IY, IB can be transformed into 2 phase currents alpha beta as shown here. Again, you can do the same thing on the 3 phase voltages. So, you have VRN, VYN and VBN, and when we have balanced load, we have VRN plus VYN plus VBN is equal to 0, balanced star connected load. So, you can write your VR alpha like this as 3 by 2 times VRN and V beta as root 3 by 2 times VYN minus VBN. This is the space vector transformation of 3 phase voltages, which we had seen in some earlier lectures now. So, what we are going to do now is going to look at the components one by one. We are applying some voltage VRN, VYN and VBN on the machine. So, let us consider the fundamental component alone of VRN. So, we would call that as VRN comma 1 representing the fundamental component. The same the amount of fundamental voltage is applied along y axis also with a phase shift of 120 degree. So, we would call that as VYN comma 1. This VBN is the B phase line to neutral voltage applied on the load, VBN comma 1 is the fundamental component. So, let us call this as Vm sin omega t. So, this would be Vm sin omega t minus 120, this would be Vm sin omega t plus 120. So, what would be the fluxes? That is what we are going to look at now. Now, if you have your applied voltage VRN 1, that is the sinusoidal, mean the fundamental voltage applied, that is equal to the IR drop. This Rs is the stator resistance and IR 1 is the fundamental current through R phase. So, this is IR 1 Rs plus d psi R 1 by dt. This is the rate of change of flux linkage now. What we can do in most cases is, this term is negligible compared to the second term, we will simply call this as d psi is approximately d psi R 1 by dt. So, that is the R phase voltage, fundamental voltage is approximately equal to the rate of change of R phase flux linkage. So, this neglecting IR drop is a standard assumption which is actually valid at higher speeds. This basic that V wave drive idea is based on that, constant volts per hertz drive is actually based on that. If you ignore IR drop, you have your flux linkage and this would turn out to be the product of flux and frequency. So, your flux is approximately proportional to voltage by frequency, and that is why you do a constant V wave control. Those who may be familiar with the constant V wave for volts per hertz will know that constant V wave works well at a fairly high speeds, but when it comes to lower speeds there is some kind of flux weakening. So, a certain voltage boost is given. So, what happens there is this IR drop becomes significant at low speeds of the motor drive or low modulation indices. This quite a few of you who have done something on motor drives will be fairly familiar with that. So, if you do not, unless you consider low modulation indices and low modulation frequencies of the drive, IR is negligible is a fairly valid assumption, that is all that I am trying to say now. So, this voltage is d psi by dt. The same thing can be said about the Y phase fundamental voltage and the corresponding Y phase flux linkage, the B phase fundamental voltage and the corresponding B phase flux linkage now. Alright. So, these are about the fundamental fluxes now. So, this 3 phases when you do a space vector transformation, so you get a voltage vector V 1 of magnitude 3 V m by 2. So, if you go back to that, you can see this here. So, your V alpha is equal to 3 by 2 times V r n. If your V r n is V m sin omega t, V alpha is going to be 3 by 2 times V m sin omega t, and you can see that the magnitude of your vector is 3 by 2 times the peak value of V r n. That is what you are getting here. So, the peak value of V r n fundamental is V m. So, the voltage vector is of magnitude 3 V m by 2. Okay. So, the flux vector, that is the 3 phase flux linkages are there, fundamental fluxes are there, you can actually transform them into the space vector domain to get your psi 1. So, this psi 1 will be nothing but whatever is this magnitude of the voltage vector V 1 divided by omega, that is what it will be. So, this produces a magnetic field, it is a revolving magnetic field. We are talking of only the fundamental components at this point of time, the other components we are going to take up one by one. So, the fundamental component alone, what happens, it produces a flux linkage whose magnitude is given by that, and it rotates at the fundamental frequency omega. So, next if you look at the fifth harmonic voltage. So, other than the fundamental, there are many harmonic components. So, let us just look at the fifth harmonic for now. So, the fifth harmonic, let us say it has some peak value V 5. So, V r n 5, V y n 5, V b n 5 are the fifth harmonic components of V r n, V y n and V b n respectively, and these are of course balanced at 3 phase sign, the sense all of them have same amplitudes, they are at the same frequency, they are actually phase shifted. So, what you are actually doing is from V r n and V y n is time shifted from V r n by 120 degree. So, if you replace omega t in V r n by omega t minus 120, you are going to get the corresponding y phase thing. So, we say that it is V 5 times sine of 5 omega t minus 120, 5 times omega t minus 120. So, again your fifth harmonic in V b n would be V 5 times sine of 5 multiplied by omega t plus 120. So, this is what you will have now. So, if you do this, this is V m sin 5 omega t, this is 5 times omega t minus 120 is sine of 5 omega t minus 600. And we know the periodicity is 360 degrees now. So, or 720. So, this is same as 5 omega t plus 120 degree, because I am just adding 720 degrees to this 5 omega t plus 120. The same way if I do this here, this is 5 of omega t plus 120. So, what I have is V 5 times sine 5 omega t plus 600. So, I can subtract 720 degrees here. So, it becomes V 5 times sine of 5 omega t minus 120. So, what happens here, if you look at the earlier case, it is omega t, y phase is omega t minus 120, b phase is omega t plus 120. So, now if you look at here, y phase is omega t 5 omega t plus 120, b phase is 5 omega t minus 120. So, you can see that the phase sequence has been changed. So, what happens when the phase sequence changes? Many of you who know basic induction motor control certainly know this. If you just interchange 2 of the terminals, the motor will start running in the opposite direction. So, the same way what I mean, that essentially means that these fellows, the fifth harmonic voltages, are going to produce a magnetic field which actually runs in the opposite direction, because you know they give you a different phase now. So, they produce a magnetic field in the opposite direction now, which we will look at it in little more detail as we go by. So, this is the 3 phase fifth harmonic flux. How is it related? The IR drop is negligible is even more valid here, because there is not so much of current and the resistance itself is negligible compared to the reactances. So, the fifth harmonic voltage is equal to the rate of change of the fifth harmonic flux. So, the same thing is for R phase, Y phase and B phase. So, we get some d psi r y etc. now, and psi r 5 is sinusoidal. So, d by dt of that is again sinusoidal, of course, this is sinusoidal. So, what you will only have is you will have a omega term coming up here. So, you will have the psi r 5 amplitude will be V r n 5 by omega. So, this can roughly be written as omega multiplied by certain amplitude here. So, you have this equation. So, as I mentioned before, it produces certain amount of flux and that revolves in the opposite direction. Okay. So, the psi phi is going to be V 5 times V 5 divided by phi omega, that is what you get from here. So, you get the psi phi is equal to V 5 by phi omega, and this fifth harmonic, as we had seen earlier, is also causing currents, fifth harmonic current. The fifth harmonic current can be given by V5 by 5 omega L, where L is the stator leakage inductance plus the rotor leakage inductance of the induction machine. So, okay. So, this is what I mean, in some sense these two equations sum up the effect of the fifth harmonic voltage applied on the machine. This is the fifth harmonic flux and this is the fifth harmonic current. So, in the flux it is interesting to see, this is the magnitude, what is the frequency and what is the direction. As we already saw, the direction of the flux is opposite to that. This is in the anti-clockwise direction, whereas this is in the clockwise direction. So, this revolves in this direction, and at what frequency? It is 5 omega, because that is the applied frequency. So, this revolves at 5 omega. So, the relative speed, if you look at, is 6 times omega, that is the relative speed of the fifth harmonic flux with respect, or the fifth harmonic magnetic field with respect to the fundamental magnetic field is 6 times omega. So, this the causes what is called as sixth harmonic torque, as we would see a little later. Now, let us also look at the seventh harmonic voltage. So, the seventh harmonic voltage, let us in the R phase we will call it as VRN comma 7, as we have seen now VRN stands for the R phase line to neutral voltage, the instantaneous voltage. This 7 stands for the harmonic order. So, this is the seventh harmonic component. The same way this is VYN 7 and VBN 7 now. Let us say the amplitude of the seventh harmonic component is V7. So, this is some V7 times sin 7 omega t is, let us say, is the VRN now. And what is VYN of 7? It is V7 sin 7 multiplied by omega t minus 120, and that is V7 sin omega t minus 840. So, you can add 720 degrees to that, 360 or 720 whatever, because it is periodic over 360, the whole thing is periodic over that. So, if you add 720 degrees to that, you get V5 sin omega t minus 120 degree. Now, if you look at the seventh harmonic of B phase, that is going to be V7 sin of 7 times omega t plus 120, which is actually V7 sin 7 omega t plus 840. So, this is plus 120 degree. So, you can see that the phase sequence is same as fundamental. This is R phase as 7 omega t, Y phase is 7 omega t minus 120, and the B phase, its phase angle is 7 omega t plus 120 degree. So, this is same as the fundamental, the phase sequence is same as the fundamental, but the magnetic field, so it will also revolve in the same direction as the fundamental. So, you can do this analysis for 11th and 13th. For 11th, you will find that it is like the fifth harmonic, it produces a magnetic field in the opposite direction, whereas for 13th, like 7th, it will be producing a magnetic field in the same direction as the fundamental. So, the same way you can look at 17 and 19, 23 and 25. So, you can actually generalize all this, this is what you will get if you go looking by harmonic after harmonic. So, all the harmonics which are like 6k minus 1, where k is an integer like 5, 11 etc., they would produce revolving magnetic fields in opposite directions, and the other ones would produce in the same direction as this now. So, let us look at only 5th and 7th, so that they are representative of the rest of the harmonics, and also 5th and 7th are the most prominent ones in low frequency case, because higher the harmonic voltage, the harmonic currents are anyway better filtered. Therefore, the problems of higher harmonics are a little lower than the problems caused by the lower frequency voltages. So, let us focus on 5th and 7th here and go a little further. So, the 7th harmonic certainly drives certain amount of produces a magnetic field, and that is like V7 by 7 omega. So, the 7th harmonic voltages, the 3 phase voltages, you transform them into the space vector, you will get some voltage vector V7 magnitude. So, this V7 by 7 omega would be the magnitude of the 7th harmonic flux vector, and the 7th harmonic voltage also causes some I7 is equal to V7 by 7 omega L. So, this causes the there is certain amount of for 7th harmonic flux, there is certain amount of 7th harmonic current, both are being caused by the 7th harmonic voltage being applied here now. Now, if you look at here, this is 7 omega and this is what I am giving as psi 7, it is revolving in the same direction as the fundamental, but at a speed 7 omega. So, interestingly, the relative speed between psi 7 and psi 1 is same as the relative speed between psi 5 and psi 1. Here the relative speed is 6 times omega, here also the relative speed is 6 times omega. Excuse me. Therefore, this also contributes to the 6th harmonic torque. All right. So, let us look at a little closer. what is this torque generation? So, we have looked at voltages, you looked at currents, and today we have started looking at fluxes, and now we are talking of torque. So, what is this torque? Let us first look at the steady torque produced by the fundamental components. That is, you have sinusoidal machines, induction motors with fed with sinusoidal voltages, they produce steady torque, right. So, these fundamental voltages we are applying, they cause fundamental currents and fundamental fluxes. These fundamental currents and fundamental fluxes would also produce a steady torque. This is what we are first trying to get an understanding of. Okay, how does it happen? It's of course it's qualitative, but let us try to understand something here. The stator magnetic field revolves at fundamental frequency. What are you doing? You are applying a 3-phase voltage on a 3-phase winding, and it produces a revolving magnetic field. At what frequency? It at the fundamental frequency. The amplitude of that, the strength of that magnetic field is given by V by omega, that is the ratio of your stator voltage to the stator frequency, and the magnetic field itself rotates at the fundamental frequency. So, what happens now is it rotates. Because of its rotation, there is something, there is rotor currents, there is induced, and this is slip frequency. What is happening to the rotor? The rotor sees an MMF wave moving past. So, there is some EMF induced in the rotor, and the rotor is shorted, and therefore, certain currents are produced. And at what frequency is these currents are produced? That is at the slip frequency. We know that the rotor is not rotating at the same speed as the stator magnetic field. The rotor speed is lower than that, in the motoring operation it is lower than that. So, the rotor is lowering. So, there is something called slip, that is the synchronous speed minus rotor speed divided by the synchronous speed. So, that is slip. So, there is certain slip frequency. If let us say the fundamental frequency is 50 hertz and the rotor's speed is equivalent to 49 hertz, the slip frequency is 1 hertz. So, the rotor sees an MMF wave at 1 hertz frequency, and there is an induced EMF of 1 hertz frequency, and therefore, there are rotor currents induced which are at this slip frequency 1 hertz, let us say. Now, these are currents flowing through the rotor. So, they cause magnetic field. So, this magnetic field is again going to be revolving. Why? Essentially because the rotor is also equivalent to a 3-phase winding, and 3-phase currents are flowing through that. So, but the only thing is the currents are of slip frequency. So, the rotor magnetic field will rotate at slip frequency with respect to the rotor, slip frequency with respect to the rotor. So, the rotor magnetic field will rotate at something like, let us say, 1 hertz with respect to the rotor. But you see that the rotor is already rotating at 49 hertz, a frequency, a speed equivalent to 49 hertz. So, the rotor magnetic field revolves at the fundamental frequency with respect to the stator. So, the rotor magnetic field it actually revolves at slip frequency with respect to the rotor, but the rotor itself is rotating. So, if you look at stator as the reference, the rotor magnetic field also revolves at the fundamental frequency. Therefore, you have the rotor magnetic field rotating and also the stator magnetic field rotating at the fundamental frequency. So, you need two magnetic fields which are actually revolving at the same frequency, and that is what produces a steady torque. Why? Because the torque is nothing but a kind of cross product of these two magnetic fields. So, cross product means it depends on the strength of the first field and its strength of the second field and sine of the angle between the two fields. And if in a steady state situation, there are two steady magnetic fields, or their relative speeds are equal, they have a constant angle between the two. Let us call the angle as delta. So, some sine delta, that sine delta is a constant. Whereas, if these two magnetic fields are revolving at different frequencies, what will happen? That delta will keep on changing, therefore, sine delta will keep on changing, and so over a period of time it will average to 0. So, if these two magnetic fields are not at the same frequency, they are going to produce a torque which is actually pulsating in nature. This is what we are going to study, because the harmonic voltages are actually causing that. So, when you talk of sinusoidal operation of the machine, or when you talk of the effect of the fundamental voltages on the machine, what happens? The stator magnetic field is at the synchronous frequency, the rotor magnetic field is also at the synchronous frequency. So, these two together work and they produce a steady magnetic field, it produces a steady torque. So, it produces a steady torque due to the interaction of these two fields now. Okay. So, this also explains why your induction motor is self starting. This is a question that is often asked by students, or students are asked this question now. So, one way to look at it is, let us say the induction motor is at standstill. Let us say it is at standstill. Let us say some 50 hertz has been applied here. This is fundamental frequency. Let us say sinusoidal frequency is applied. It says 50 hertz is being applied now. So, if 50 hertz is being applied, the rotor is at standstill. So, what is the rotor current frequency induced? What happens to the rotor? The rotor sees a 50 hertz wave moving past it, and therefore, there is an induced EMF in the rotor which is 50 hertz frequency, and the rotor has got a shorted path, it is a shorted one. So, therefore, the rotor currents are going to flow, and what is the rotor current frequency? 50 hertz. So, the rotor will now produce a magnetic field which rotates at 50 hertz while the rotor is at standstill. Therefore, the stator magnetic field is at fundamental as 50 hertz, the rotor magnetic field is also at 50 hertz, and these two magnetic fields, since they are at the same frequency, they produce a steady torque, and therefore, there is a non-zero starting torque produced by an induction motor, because it produces a stator magnetic field and also rotor magnetic field, both of them being at the same frequency. So, it starts rotating now. So, there is a starting torque. Let us say the motor starts rotating, what happens? Let us say the rotor has picked up some speed, let us say it is running at a speed equivalent of 1 hertz. So, what happens now? The stator magnetic field continues to be at the same 50 hertz. Now, the rotor is now rotating at 1 hertz equivalent of frequency, it has slightly increased. So, now what is happening? The slip frequency is 49 hertz. So, 49 hertz of current is actually, the rotor currents are now would be 49 hertz. So, these rotor currents induced will produce a rotor magnetic field which will rotate at 49 hertz with respect to the rotor. So, if the rotor magnetic field is rotating at 49 hertz with respect to the rotor, and the rotor itself is rotating at a speed equivalent to 1 hertz, then the rotor magnetic field is rotating at the fundamental frequency, I mean at 50 hertz with respect to the stator. So, the rotor has picked up speed, it has come to 1 hertz, still the rotor magnetic field and the stator magnetic field are both at 50 hertz, and therefore, the machine continues to produce torque. So, the machine goes on accelerating. So, the rotor speed may be 10 hertz, in that case the slip frequency will be 40 hertz. So, the rotor magnetic field will still be 50 hertz, same as the fundamental. The rotor has accelerated further, the rotor has gone to say something like 25 hertz. So, during that time, so the rotor magnetic field is at 25 hertz, the rotor itself is rotating at 25 hertz. Once again, the rotor magnetic field with respect to the stator is 50 hertz. So, both the stator and the rotor continue to produce at the same thing, and the rotor goes on accelerating till when? Till it reaches a speed which is reasonably close to your fundamental frequency, that is what you call a slip. It will not reach the slip, I mean it will not reach the same speed as the synchronous, what is called as the synchronous speed. If it reaches the synchronous speed, then what happens? The slip is 0. When the slip is 0, the induced EMF in the rotor actually becomes 0, and there are no currents, and no appreciable currents, and there is no appreciable torque. So, it goes to something close to 50 hertz, maybe 49.8, 49.5, that depends on the torque demanded, how much, I mean depends on the load torque. So, it goes to some frequency which is close to 50 hertz like 49 or 49.5. So, the slip frequency is 0.5 or so. So, the slip frequency at which it settles down is actually dependent on the load, or it is a measure of really the load torque. So, this is how you can actually explain the why an induction motor is really starting or self starting. So, whereas this is not true with a synchronous machine. A synchronous machine, what happens? The stator frequency is very similar to an induction motor. So, it is a 3-phase winding, you may be applying 3-phase voltages. So, it produces a revolving magnetic field at synchronous frequency, but how about the rotor? The rotor is at standstill. So, if you excite DC through that, it is not producing a revolving magnetic field at synchronous speed, therefore, it cannot start. But if you have done something and made sure that the stator and the rotor are rotating at the same speed, that is the rotor is also rotating at the synchronous speed, the rotor carries DC, therefore, the rotor magnetic field will also be at the synchronous speed, the stator magnetic field is also at synchronous speed, and then the synchronous machine starts producing torque. So, any machine can produce a steady torque only when the stator magnetic field and the rotor magnetic field are kind of stationary with respect to one another, only then it can produce a steady torque now. Alright, this is a DC machine does it in much simpler fashion. So, it does not rotate at all. So, there is always a stator magnetic field, there is a rotor magnetic field or the armature magnetic field, they are in quadrature. So, when the torque increases, the armature field is made stronger, and the torque produced there is actually an interaction of these two things. So, most machines which produce an alignment torque, except for machines like switched reluctance machine which actually work based on the principle of reluctance torque, this is valid for all of them. That is, they produce magnetic fields, there is stator magnetic field, there is rotor magnetic field, and both of them actually either are stationary or both of them are rotating at the same frequency, and that is how it produces now. So, with this kind of basic understanding of torque production, let us look at what happens because of all the harmonics we are applying. When you are feeding an induction motor from an inverter, you are applying not only the sinusoidal, the desired sinusoidal, which is called the fundamental, you are also applying many of the harmonics. So, these are like 5th, these are 7th, 11th, 13th and so on and so forth, and these are considerable when you are operating the inverter at a low switching frequency like 450 hertz with the fundamental itself being 50 hertz. So, these are all significant. So, what happens to the stator this thing now fundamental we have seen, let us say the 5th harmonic. The 5th harmonic, as we saw, it is going to drive some 5th harmonic current. The stator is going to draw 5th harmonic current, no doubt about it. It is also resulting in 5th harmonic flux. It is also resulting in a magnetic field, and that magnetic field, as we saw, is rotating at a frequency 5 omega and in the opposite direction. Hence, I have indicated it as minus 5 omega. So, the 5th harmonic voltage results effectively in a magnetic field which is rotating at 5 omega in the opposite direction. Now, next you have the 7th harmonic. What does the 7th harmonic do? It also produces a magnetic field, rotating magnetic field. It is, of course, it is not as strong as the fundamental, but whatever the strength may be, it produces a magnetic field. And what frequency the magnetic field rotates at? It rotates at 7 times omega and in the same direction as the fundamental, and therefore, I have shown it by a positive sign. Then similarly, for 11 and 13 you will see that it is minus 11 omega and this is 13 omega, all right. So, you have these frequencies going around like this, all right. Now, so if you have a harmonic pair, you will find that in one of that it will be negative, the other one will be positive. So, it goes on like that, all right. If you have a frequency omega, magnetic field omega, and the rotor is rotating at omega r, the rotor sees an MMF wave moving past it at frequency omega minus omega r. So, the stator magnetic field is seen as an MMF wave which moves past the rotor at a speed omega minus omega r. Therefore, the induced EMF is at the speed omega minus omega r. This is what we were calling at slip frequency a few minutes back. So, it actually does this, and therefore, slip frequency EMF and there is slip frequency current and whatever flows through this now. At the same time, if you have minus 5 omega r, so this also produces a magnetic field, but the rotor is rotating at the same omega r. So, you should remember one thing, we say that there is a steady torque and therefore, motor runs at steady speed is understandable. If we say there is a pulsating torque, then one would expect the speed also to pulsate, right. But what we are assuming is, though there is a pulsating torque, the speed is fixed, that is the motor is seen to have a high inertia. Therefore, even if the torque produced is there is a significant pulsating ripple content there, it does not cause the speed to change significantly is an assumption. So, we assume that the rotor is at a constant speed, it is not really affected by the pulsating torque. So, the rotor is rotating at omega r only, and therefore, the MMF wave whatever is corresponding to the 5th harmonic, it is moving past the rotor. So, it is like minus 5 omega minus omega r. So, actually if you see the induced EMF will be 5 omega plus omega r would be of that frequency in the rotor, and such rotor currents of 5 omega plus omega r will be flowing through that because of the 5th harmonic. The same way the 7th harmonic which is produced a 7th harmonic magnetic field. So, it is 7 omega minus omega r. So, this is rotating, this 7, that is the 7th harmonic voltage applied to the stator causes a magnetic field rotating at 7 times the fundamental frequency, and the rotor itself is rotating at omega r. So, this magnetic field moves past the rotor at a speed of 7 omega minus omega r, and therefore, there is an induced EMF of frequency 7 omega minus omega r and induced currents also of that frequency in the rotor. The same thing can be said about the other frequencies, minus 11 omega, okay, this should be minus omega r, there is an error here. All right. So, you can see that the rotor magnetic fields are at the same frequency with respect to that. This is also here, there is some. So, now does the rotor produce a magnetic field? Yes. Why? Because the MMF waves are moving at these frequencies, and therefore, there are induced EMFs at these frequencies, and the rotor provides a shorted path, and therefore, there are induced currents at these various frequencies. Every one of these frequency current is going to produce a magnetic field, and this magnetic field is going to be rotating at a speed omega minus omega r with respect to the rotor. this is going to rotate at a speed minus 5 omega minus omega r with respect to the rotor. This is going to cause magnetic field rotating at 7 omega minus omega r with respect to the rotor. This is what I have tried to indicate now. So, these are all the speeds of these magnetic fields with respect to the rotor. What would be the speeds of these magnetic fields with respect to the stator? It is back to, you add omega r to this. So, the rotor itself is rotating at omega r. So, the rotor magnetic fields with respect to the stator are at these frequencies omega, minus 5 omega, 7 omega, minus 11 omega, 13 omega. So, just let us take a look at it again. See, this is a fifth harmonic voltage. What does a fifth harmonic voltage do? It produces a fifth harmonic, it produces a revolving magnetic field, because it is also sinusoidal, it is also balanced sinusoid. It is applied to 3 phase winding. So, it has to produce a magnetic field, but the only thing is the magnetic, the field strength is different, and it rotates at 5 omega, and it is at in the opposite direction. So, the fifth harmonic voltage produces a revolving magnetic field 5 omega, which revolves in the opposite direction, and the rotor is rotating at omega r. The relative speed of this fifth harmonic magnetic field and the rotor is minus 5 omega minus omega r. So, the induced EMF is of this frequency 5 omega plus omega r inside in the rotor, and therefore, there are induced currents of the same frequency 5 omega plus omega r, and therefore, the rotor produces magnetic fields which rotates at this frequency minus 5 omega minus omega r with respect to the rotor, and therefore, it produces minus 5 omega with respect to the stator. So, you can see that the stator magnetic fields are at some frequency, the rotor magnetic fields are also there at these frequencies. The only thing is, this is a strong magnetic field and this is also a strong magnetic field, therefore, they will produce considerable torque, whereas this magnetic field and this magnetic field, they are not strong enough, or any harmonic, for example, take fifth harmonic here and seventh harmonic here, there this is low and this is, this is weak and this is also weak. So, you could actually ignore all the interactions between the between a magnetic field produced by a harmonic in the stator and a magnetic field produced by a harmonic in the rotor. Their interactions can all be ignored. You can only consider these two, they produce the fundamental, and you can consider the interaction of this field with any of these, that will give you some harmonic. Similarly, you can consider, that will give you the pulsating torque. You can consider the interaction of this with any of these, that is also going to give you the pulsating torque. So, this is where we are going to do this now. So, one way to look at it is, you can look at the magnetic field, what do you mean by magnetic field? We try to look at it. So, you can either look at it as a flux or certain amount of current. So, one way to do that is to look at it as the the stator side flux, for example, and the rotor side current. So, the stator magnetic field, for example, if you are looking at the fundamental magnetic field by the stator, you can actually look at the fundamental flux corresponding to the stator, and the rotor magnetic field can actually be represented by the rotor harmonic currents, and so you can consider the interaction between the fundamental flux and harmonic currents, say the stator fundamental flux and the rotor harmonic currents. Similarly, these will produce pulsating torque. Why? Because this is one magnetic field, this is another magnetic field. This fundamental flux corresponds to that steady magnetic field, which is at omega. The harmonic currents, they are magnetic fields which are actually rotating at different frequencies. So, the angle between these two magnetic fields keeps on changing and sinusoidally, if delta is the angle between the two, it varies as sine delta, and that is an alternating function. So, it averages to 0. So, there is no steady torque produced by that, but there is a pulsating torque produced by this. So, we are going to, but and when I am saying magnetic field, I have to represent it either in terms of flux and in terms of current. So, we will normally say it is an interaction of one flux, say the stator side flux and the rotor side harmonic current. So, in the stator side flux, we can say the fundamental flux on the stator side and the harmonic currents on the rotor side. We can look at these interactions. Similarly, we can also look at the interaction of the fundamental current. So, let us say the rotor side fundamental current and then the stator side harmonic fluxes. You can also look at the interaction of harmonic fluxes and harmonic currents. So, this is basically interaction between two harmonic fields, which is actually magnetic field produced by some stator harmonic and some rotor harmonic. As I told you before, this is quite weak and therefore, we can always ignore this. This is perhaps the strongest. Why? Because your fundamental flux is always near 1 per unit, near 100%, and the harmonic current. If you look at the harmonic current, what causes that harmonic current? It is basically some harmonic voltage divided by the harmonic reactance now. in the case of if you consider harmonic current and harmonic flux, they are essentially same, because they are all both are related to the harmonic voltage. But here it is harmonic voltage divided by, let us say, the magnetizing inductance. This is the same harmonic voltage divided by the leakage inductance. So, to put it in very simple terms, if you magnetizing inductance is much bigger and this is leakage inductance is much smaller. So, when you divide the harmonic voltage by magnetizing inductance, what you get is small actually. So, whereas this is considerable because you are dividing it by leakage inductance. If you are going to express the inductances in per unit terms, this leakage inductance is going to be very small. Therefore, that harmonic voltage divided by leakage inductance is going to be bigger, whereas harmonic voltage divided by the magnetizing inductance is going to be lower. So, that is a simple argument that one can give to say why this will be more dominant than that. So, what we would normally actually both could be considered, but normally this is the more predominant term that you would actually look at now. So, you can see that you have the fundamental flux and it interacts with fifth and seventh harmonic. Fundamental interacting with fifth harmonic current would, for example, produce sixth harmonic torque, and the fundamental interacting with the seventh harmonic would also produce the sixth harmonic torque. Again, you have fundamental flux, it would interact with the 11th and 13th. So, the relative frequency is still 12, that is the interesting point. It is fundamental, it has a magnetic field in one direction, this is 11th harmonic is 11 omega in the opposite direction, and this is the 13th harmonic produces 13 field at 13 omega in the same direction. The relative speeds between the magnetic field is always 12 here. So, it produces a 12th harmonic torque, and similarly you will have 6, 12, 18, 24 etc. These would be the harmonic torques produced in a motor. The motor, the applied voltages are 5th, 7th, 11th, 13th etc. like 5th, 7th, 11th, 13th etc. So, the harmonic currents are also 5th, 7th, 11th, 13th etc. But interestingly the harmonic torques are of order 6, 12, 18, 24 etc. The 5th and 7th interacting with fundamental produces 6, the 11th and 13th harmonics interacting with fundamental produces 12th, and it so goes on and so forth now. So, we have some interesting papers, it is actually very old, it is a seminal paper, original work in this area, and to actually do the details with the per unit equivalent circuit of an induction motor, it is possible for you to calculate how much pulsating torque it is going to produce, for example, as a rate percentage of its. Let us say when you are fed with a square wave, or when you are fed with a particular kind of PWM waveform, how to calculate the sixth harmonic torque, for example. It is possible to do that using the equivalent circuit of induction motor. This is one seminal work which actually explains how to do that now. I would strongly suggest this as a reference that you could go through to understand how such calculations can be done here. So, I have covered the preliminaries here, there can be a more detailed understanding and you can actually do it quite quantitatively. And the other reference is the lecture notes by Professor V. T. Ranganathan, this is lecture notes on electric drives. So, this also deals with this topic of pulsating torque and how you would go about calculating, and Professor R. Krishnan's textbook on electric motor drives also discusses something about it here. So, about how exactly you evaluate, you need to go into the details of the machine, and which these papers can actually give you. So, this being a PWM oriented course, I would want to give some idea on how you can avoid that torque. This is actually a difference. This sign has come out a little funnily here. So, this is actually the difference now. So, what happens is you can look through based on our previous discussion and these references, you can see that the sixth harmonic torque is produced by the interaction between the fundamental flux and the fifth and seventh harmonic currents. So, the fundamental flux and the fifth harmonic current produces some sixth harmonic torque. The fundamental flux and seventh also this thing. If this fifth and seventh have certain phase relationship and certain amplitude relationship, then it is possible that your T6 can become 0. So, the amplitude relationship can be borne out very easily. If you know the fifth harmonic voltage, this is going to be V5 by 5. I5 is proportional to V5 by 5, because the fifth harmonic voltage has a reactance, this 5 times omega L. This is going to see a reactance 7 times omega L. So, I7 is proportional to V7 by 7, and if let us say they are actually in phase, that is whenever the fundamental is crossing 0, fifth is also crossing 0, then seventh is also crossing 0, then you can just take the difference, you can subtract this from that now. So, this part is proportional to whatever is given by the fifth harmonic, and the psi 1 V7 by 7 is a measure of the sixth harmonic torque corresponding to that. These could be such that if their amplitudes are chosen such that this cancel out, it is possible that you can have 0 sixth harmonic torque. So, this is like we eliminated the selective harmonic voltages. If you remember the problem earlier, we have two variables here, alpha 1 and alpha 2 in one quarter cycle. I am just showing one quarter cycle of this. So, you have two variables, you can write two equations. You can write an equation for the fundamental voltage in terms of alpha 1 and alpha 2. You can write down an equation for fifth harmonic in terms of alpha 1 and alpha 2, and you can solve that and you get your alpha 1 and alpha 2. So, if you use that alpha 1 and alpha 2, you would have managed to get the fundamental, decide fundamental, and also eliminate your fifth harmonic. So, it is possible for you to get your decide fundamental and eliminate one harmonic voltage by going in for this alpha 1 alpha 2. The same way, the only procedure that I am suggesting is, instead of the first equation is V 1 is the desired value. The second equation, instead of saying V 5 is equal to 0, we will say T 6 is equal to 0, or V 5 by 5 minus V 7 by 7 is equal to 0. That should be the second equation. If you use those two equations and solve for this alpha 1 and alpha 2, you will be ending up with this sixth harmonic elimination. And we can actually look at it on this plane which we had looked at long back. For example, this alpha 2 and alpha 1 are the switching angles, and this corresponds to square wave operation if you recollect our earlier lectures on this low switching frequency PWM, and this line would correspond to something like V 1 is equal to 0 per unit. So, a particular fundamental voltage will go like this, that is all the points along this line would actually give you a particular fundamental voltage now. Then we also looked at the sixth or fifth harmonic voltages and so on and so forth, right. For example, if you look at the points where V 5 is equal to 0, you will have some curve like this. This is a point where you will have all V 5 is equal to 0. Again, you may have some curve going like this, where your V 5 is equal to 0. So, the same way, you look at V 7 is equal to 0, you will have a situation where this is V 7 is equal to 0, this is some V 7 is equal to 0. These are lines where V 7 is equal to. We did all this when we did the selective harmonic elimination and so on and so forth now. So, on this plane, it is possible for you to select points where the sixth harmonic torque is 0. An example would be this point. This is an example. So, again if you look at both V 5 and V 7 are 0, you will see some points in the vicinity where V 5 by 5 minus V 7 by 7 is equal to 0. So, you can solve for this equation. V 1 is equal to, for example, 0.8 per unit, and V 5 by 5 minus V 7 by 7 is equal to 0 to eliminate sixth harmonic torque. You can try this as a home exercise, and we can anyway discuss this elimination in our next lecture before we go on to the high switching frequency. So, I thank you very much for your attention, and I thank you very much for your interest. I hope you found this lecture interesting, and I am looking forward to your participation in the next lecture on this topic. Thank you very much.